This is Steve Denenberg. We are continuing our discussion of issues surrounding the physics of momentum. Next, we're going to talk about the center of mass. A little introduction before we get to the simple math. You can think of the center of mass of an object as the place where you can put a fulcrum and the object will balance. So for this uniform horizontal bar, it's in the middle of the bar. Place a fulcrum underneath the middle, and in our gravitational field, that will balance. But you can't just always put it in the middle. This is my terrible drawing of a hammer with a heavy metal head and a much lighter wooden handle. This thing won't balance if you put it right in the middle. You have to put the fulcrum rather close to the metal head in order to get it to balance. An object that is geometrically regular will have its center of mass in the centroid, which is the middle. If you have a square, the center of mass is in the middle. If you have a circular disc, it's in the middle. If you have an equilateral triangle, it's in the middle. The center of mass doesn't even have to be on the object. If you have a frame that is regular, here's the frame, the center of mass is here, not even on the object. An object, or a system of objects, will behave as if all of its mass is concentrated at the center. One thing about the center of mass is that it's the place where you can push that won't add a rotation to the object. So for example, our bar, if you apply a force right here, the bar will accelerate upward, but it won't rotate. If you have a flat plate square with a center of mass here, and you push in the center of mass, our plate will accelerate this way. Whereas if you push over here, off of the center of mass, you can expect our plate to rotate while it's moving. A system of objects also has a center of mass. Here's our system. 2 billiard balls. We have an M here and an M here. And maybe it's pretty easy to see that the center of mass of this system is right in between them. If the masses are different in size, or if there's more than 2 of them, then we have to think a little bit harder about where the center of mass is. So let's figure that out. So here's our system. We have a 6 kilogram mass here, and we have a 2 kilogram mass here, and their centers are separated by 3 meters. Where is their center of mass? Well, I'm going to guess it's over here somewhere. So let's see if that works with our fulcrum idea. Let's pretend they're on a seesaw, or let's pretend they're attached by a massless rod. And let's say that this distance is x, how far the 2 kilogram mass is from the fulcrum. We've done these problems before without actually thinking about center of mass, more about torque. We've touched on torque even though we haven't done circular motion yet. So we have a 2 kilogram mass putting a force of 20 newtons here, and that has a lever arm of x trying to push the seesaw down this way. And over here we have a 6 kilogram mass putting a 60 newton force here, and its lever arm here is 3 minus x. And it's trying to rotate our seesaw this way. So let's work that out. We have 6 times 3 minus x equals 2 times x. And we get x equals 2 1/4 meters. So sure enough, the center of mass is much closer to the larger of the 2 masses. But this seesaw thing won't work very well if we're trying to find the center of mass of a system of big and little particles that might be all over the place. So let's see how to do it right. Here I'm going to draw a coordinate system. Here's our y-axis, and here's our x-axis. Here's 0 on the x-axis. 1, 2, 3, 4, 5, 6. I'm going to put our 6 kilogram mass on the 2 meter point. And we said the 2 kilogram mass was 3 meters distant. So that'll be at the 5 meter point. So we are going to sum not just the masses but the mass times the distance from some reference point, and that will be 0 on the x-axis. And then we're going to divide by the total mass. What do I mean by that? Okay, we have a 6 kilogram object at the 2 meter point, and we have a 2 kilogram object at the 5 meter point. And we're going to divide that by the total mass, 6 kilogram plus 2 kilograms. And that's where our center of mass is. Let's work it out and we'll talk about it some more. So that's 12 plus 10 is 22 kilogram meters divided by 8 kilograms. And the units are working out okay as well. And that equals 2 3/4 meters, which puts our center of mass right here, where we thought it was, closer to the bigger one that we would expect. We're taking the sum of the mass of each object times its distance from some reference point and dividing it by the sum of the masses, which is just the total mass of the system. And that gives us the location of the center of the mass. Now remember when we were working with gravitational potential energy, we said that if something fell from here to here, it was the change in position that was important, not whether we said it went from 0 to negative 10 joules, or whether it went from 10 joules down to 0 joules. It was the change that was important. Here too, in computing the center of mass, no matter where you set your reference point, you'll wind up with the same answers. So let's try this one again, but this time I'm going to set the origin as going right through the larger mass and see what happens. So here's our positive x-axis. Now we have a 6 kilogram mass at the origin, and our 2 kilogram mass is still 3 meters away from it. So let's take the sum of mass times distance and divide it by the sum of the masses of the particles, the total mass. So over here we have 6k, and its distance along the x-axis is 0, plus 2k, and its distance is 3. And the sum of the masses is still 8k. So now we have 0 plus 6 equals 6 kilogram meters divided by 8 kilograms, and that's 3/4 of a meter. Well, look, here's 1 and 2, and here's our 3/4. It wound up in the same place relative to the two masses. It didn't matter where we put our reference point. When we look at the geometry of the system, the center of mass is going to end up at the same spot. And just for practice, looking at changing signs, let's try this yet again. And this time, here's x equals 0. Here's the positive x-axis. We're going to put the axis through the 2 kilogram object. And over here, at negative 3, we've got the 6 kilogram object. So let's sum it up and see what happens. The sum of the masses, each mass, times its distance from the reference point, it's going to be 6 kilograms times negative 3 meters plus, and this will be 2 kilograms times 0, and the total mass is still 8 kilograms. And that equals negative 18 kilogram meters over 8 kilograms, and that's negative 2 1/4 meters. 1, 2, 2 1/4. Lo and behold, we get the same geometric location relative to our system of the center of mass. We can't change the location of the center of mass based on how we compute its location. Now take a look at this. If we say the origin is right here, and we have a 2 kilogram mass at 2 1/4 meters, and we have a 6 kilogram mass at negative 3/4 meters, when we take the sum of mass times distance, do you see what's coming? 6 times negative 3/4 plus 2 times 2 1/4, that's going to be 0. And in this coordinate system, the center of mass is going to be right at our origin. And in fact, we're looking at the definition of the center of mass. It is the location where, if you do your computation of the mass of the objects in the system times their distance from that location, and if it sums to 0, then you are at the center of mass. What if you have 4 masses? Here's our positive x direction. What if you have a mass here, and a little mass here, and a bigger mass here, and a really big mass out here? Where is the center of mass? You do it the same way, you just have more masses. Let's call this weight M1, M2, M3, and M4. And let's call these distances along the x-axis D1, D2, this is D3, D4 is much bigger. And the place where the center of mass is going to end up, we figure out by taking M1, D1 plus M2, D2 plus M3, D3 plus M4, D4 over M1 plus M2 plus M3 plus M4. And once again, you have mass times distance divided by mass. This will give you the distance. And with this reference location, that distance will define for us the center of mass of this 4-object system. It will be somewhere along the x-axis. Now, to help make this even more intuitive, let me just rearrange this equation that we just wrote. What we're saying is that the x location of the center of mass we compute by doing this. And we said that an object or a system of objects behaves as if all of its mass were concentrated at the center of mass. So I'm going to rewrite this equation like this. M1 plus M2 plus M3 plus M4 times the x location of the center of mass equals what? M1 D1 plus M2 D2 plus M3 D3 plus M4 D4. And to me at least, this makes it more obvious that all of the mass being at this location is the same as, acts the same as, if each mass is at its real location. I like that. This is how we compute the location of the center of mass. Sum the masses times their distance from the reference point, divide by the total mass. And that's like saying that in a system spaced like this, it behaves as if all of the mass is at the location of the center of mass. Now, you could probably totally predict that in computing the location of the center of mass, you do the x and y directions separately. So let's take a look. Here's the positive x direction. Here's our positive y direction. Here's our origin. And I'm going to give you a system of 3 masses. You have a 1 kilogram mass at location 2, 1. You have a 2 kilogram mass at location 4, 4. And you have a 2 kilogram mass at location 7, 3. Where is the center of mass of this system? Well, let's see. The center of mass in the x direction, let's label the masses. Mass number 1, mass number 2, and mass number 3. So this is the mass of object 1 times its distance along the x-axis from the reference place, which is our origin, plus the mass of object number 2 times its distance along the x-axis from our x-axis reference point, plus the mass of mass number 3 times its distance along the x-axis, divided by the total mass of our system. And when we work that out, we're going to get 4 4/5 meters. And then we're going to do the same thing in the y direction, taking the mass times the y component, the distance from our y reference line down here, plus this mass times how far it is in the y direction, plus the third object's mass times its distance in the y direction and divide by the total mass. And if you work it out, I won't do the math here, you're going to get 3 meters. So the center of mass of this system is at 4 4/5 along the x-axis and 3 along the y-axis. Here's our center of mass. You may have an object for which you need to find the center of mass that is a collection of regular objects. What do I mean by that? What if the object looks like this? And where's the center of mass? Well, you can have a reference plane somewhere. Well, this is a regular rectangle, so we know that its center of mass is right here. And here's another regular rectangle, and its center of mass is in there. And maybe this thing is a square, and its center of mass is right there. So really what we had before is a system of 3 objects in 3 locations. 1, 2, 3. Each has a location and a mass, and you compute the center of mass of those 3, and that lets you get the center of mass of something that looks bizarre, but maybe it's just a collection of regular shapes. Maybe something by its symmetry, maybe you have a rod connected to a circle here, to a circular disc, and by symmetry you know that the center of mass, if I drew this well, was going to be along the x-axis. So just draw your x-axis. The rod part has a center of mass right here, and the circle part has a center of mass right here. If this is uniform, its mass is going to be its area, and if this is uniform, its mass is going to be proportional to its area. So you have 2 objects, and you find the center of mass. The rod is m1, the disc is m2 in weight, this distance is d1 along the positive x-axis, and this is d2. So you have m1 d1 plus m2 d2 over m1 plus m2 equals the location along the x-axis of the center of mass of this oddly shaped item. And one more little trick. Let's say you have something that looks like this, but it's missing a little circular cutout right here. So our object is all of this material, but there's no material in that circle that I drew. Well, once again, get the mass and the location of this piece, and the mass and the location of this piece, but then you're going to have another item, which is a circular item right here, with its own mass and its own center location. But the mass of that circular item, because it's missing, because it's a cutout, will be negative. When you were computing the center of mass, you used this thing, and you added this thing. Well, now you have to subtract this thing. So if this is mass 1, and this is mass 2, and your circular cutout is mass 3, you're going to set up a coordinate system, and it's going to be m1 d1 in x and y plus m2 d2 minus m3 d3. And you'll be able to compute the center of mass of this weird system where a piece is missing. If that's not clear enough, email me. Okay, this is all pretty easy so far. Let's see what happens if we have a system that has a center of mass. We have a 3K mass here and a 1K mass here. And let's say they're separated by 4 meters. But let's say that the smaller mass is moving at 4 meters per second. What's going on with the center of mass now? Well, without dragging you through the 7th grade algebra, the center of mass of this system started out at the 1 meter point between these 2 items. After 1 second, we have our 3K mass here, and our 1K mass is out at 8. And the center of mass is now at the 2 meter point. The smaller mass has moved farther away, and the center of mass has crept out to follow it. And after yet another second, our 3K mass is still right here. Our smaller mass has moved out to 12. And if you run through the simple calculation, you'll see that the center of mass has moved out to the 3 meter point. So our center of mass is moving to the right at 1 meter per second. We're going to say that the velocity of this center of mass equals 1 meter per second in this direction. When we're looking at a static system, our center of mass was an x location, and it had a certain distance from some certain reference line. But now if it's moving, we have the velocity of the center of mass with a certain velocity, meters per second. So we are going to talk a little bit about when the center of mass is moving. And yes, indeedy do, there are FRQs in recent AP Physics 1 exams that talk about a moving center of mass. And it's so easy you're going to cry. So how do we compute the motion of the center of mass? When we were looking at the location of the center of mass, and let's just talk about the x direction right now, we took each mass and multiplied it by its position. And we said the x location of the center of mass was equal to the mass of the first particle times its distance from some reference place, plus the mass of the second particle times its distance from some reference place, on and on and on. And we divided by the total of the masses of the particles in the system. When we're looking for the velocity of the center of mass of a system, we do the same thing, except instead of looking at the location of each mass, we look at the velocity of each mass, plus the second object's mass times its velocity, on, and divide that once again by the total mass of the system. So in the example we had above, we had a 3 kilogram mass that was sitting pretty. We had a 1 kilogram mass that was moving at 4 meters per second. So let's do this computation. Mass 1 is 3 kilograms. V1 is 0 because it's not moving. This one isn't moving. So this is mass 1 times V1 plus mass 2, which is 1 kilogram, times its velocity, which is 4 meters per second, divided by the total mass of the system, 3K plus 1K. And that equals 0 plus 4 kilogram meters per second, mass times velocity, divided by 4 kilograms, and that equals 1 meter per second. And indeed, we discovered in our example that the center of mass was moving at 1 meter per second. See how easy this is? It's the same equation that we already learned for finding the location of the center of mass, but now we're able to find the velocity of the center of mass. Both masses might be moving. Let's say you have a 2 kilogram mass that's moving this way at 3 meters per second, and you have a 5 kilogram mass that's moving this way at 1 meter per second. We do it exactly the same way. The velocity of the center of mass equals, we will label this object 1 and object 2. The velocity equals the mass of the first object times its velocity. Oh, looks like we better have a coordinate system and know which direction is the positive x direction. So its velocity is -3 meters per second plus the mass of the second object times its velocity, which is +1 meters per second, because it's traveling in the direction of the positive x-axis, over, and I'm just going to say total mass since we know it's always there. So what do we have? We have -6 plus 5 kilogram meters per second divided by the total mass, which is 7 kilograms, and that equals -1/7 meters per second. So the center of mass is creeping in the negative x direction at 1/7 meter per second. You may have also noticed that when you're computing the velocity of a center of mass, you don't have to have a reference point. You just take the velocities and run them through the equation, and it comes up accurate. You don't have to select an origin along the x-axis. See, this is still very simple stuff. We computed the location of a center of mass, and now we can compute the velocity of a center of mass. Now I want to go back to our very first example of moving center of mass. And I'll remind you what it was. We had a 3 kilogram object that was sitting still, and we had a 1 kilogram object that was moving this way at 4 meters per second, and we said that the center of mass was moving in this direction at 1 meter per second. Remember that? So now we're going to do something different. We know what's happening. We know we have an object at rest, an object moving to the right at 4 meters per second. The center of the mass of the system is moving to the right at 1 meter per second. Let's pretend that we are sitting on the center of mass and seeing things how the center of mass sees it. Well, if we are sitting on the center of mass, here we are, sitting right here on the center of mass. What we see is a 3 kilogram object that's moving this way at 1 meter per second. Do you get it? In our ground reference frame, the 3K object is sitting still. The center of mass is moving to the right. Well, the center of mass and the 3K object are separating at 1 meter per second. So if you are sitting on the center of mass, moving with it, you see that 3 kilogram object moving away from you at 1 meter per second. Okay, I hope that's clear. We just changed our frame of reference. And so what do we see over here? The second object is moving to the right at 4 meters per second, but the center of mass is tagging along at 1. So if we're sitting on the center of mass as it moves, we see that second smaller object pulling away from us at 3 meters per second. It's traveling 3 meters per second faster than we are, so it's pulling away from us at 3 meters per second. See? So here we are in the frame of reference of the center of mass. We're sitting with the center of mass, so we don't think we're moving. We see object number 1 moving away from us to the left at 1 meter per second, and we see object number 2 moving to the right at 3 meters per second. What's the total momentum? Add it up. It's -1 times 3 in the positive x direction. We always need a positive x direction. Plus it's 3k times -1 meters per second. If we're looking with the positive x direction here, we always need to define the positive x direction. Plus, what's this guy's momentum? 1 kilogram times 3 meters per second. And lo and behold, that's 0. Can I try it again really quickly? If we have a 2 kilogram mass moving this way at 7 meters per second, and we have a 3 kilogram mass moving this way at 12 meters per second, if you do the math, the velocity of the center of mass equals m1 times v1 plus m2 times v2 over the total mass, and that equals 10 meters per second in, once again, the positive x direction. The center of mass of this system is moving to the right at 10 meters per second. What does that moving center of mass see? The center of mass is moving this way at 10. So here we are on the center of mass. We're moving to the right at 10. This guy's only moving to the right at 7. So he's falling behind from us. We see him moving to the left at 3 meters per second because we're getting farther away from him. We're sitting right on top of that moving center of mass. But this object on our right, this bigger mass of 3K, in our rest frame, he's moving to the right at 12. The center of mass is only moving to the right at 10, so this 3K mass is pulling away from us at 2 meters per second. He's going 2 meters per second faster than we are. And oh, guess what? You sum the momentum and you get 0 again for the total momentum of the system. What does this mean? This means if you are moving along with the center of mass of a system, and you measure the total momentum of the system, you get 0. If there's 2 masses or there's 1,000,000 masses, you have 1,000,000 masses in your system, and they have various velocities relative to each other, and the whole system is moving in some direction. If you sit on top of the moving center of mass and you measure the momentum of every particle and add them all up, you're going to get 0. Now here's an important concept that can help us out with some problems. A system of objects, like we've been talking about, 2 masses, 3 masses, 1,000,000 masses, a system of objects obeys Newton's first law just like a single object does. We said that a mass will stay at rest or will move with constant velocity without acceleration in a straight line unless acted on by an outside force. Well, we can also say that the center of mass of a system of objects will either stay at rest or will move with some constant velocity unless it's acted on by an outside force. So what does that mean? We saw a situation just now where we had a 2 kilogram mass that was moving at 7 meters per second, and our system included a 3 kilogram mass that was moving at 12 meters per second. And we said that the center of mass in between them, which we didn't care so much exactly where it was because we were talking about its velocity, we said the center of mass was moving this way at 10 meters per second. So that tells us that after they collide, whatever final velocities they have, if it's an elastic collision, if it's an inelastic collision, if it's a perfectly inelastic collision, we know that after the collision, the center of mass is still going to be moving to the right at 10 meters per second. Because the collision happened within our system of 2 objects, there were no external forces. There was nothing to change the fact that its center of mass was moving to the right at 10 meters per second. So after the collision, the center of mass is still going to be moving to the right at 10 meters per second. How might that help us? Well, right off the bat, we know that if the collision turns out to be perfectly inelastic and the 2 kilogram object winds up stuck to the 3 kilogram object, well, we know that they're going to be traveling at 10 meters per second because now it's only one object, and the speed of the center of mass is going to be the speed of that one object, and the velocity of the center of mass isn't going to change because there were no outside forces. It started out at 10 meters per second to the right. We computed it. They collided. We know it's still going to be 10 meters per second to the right. So if they're stuck together, they have to be moving at 10 meters per second. And we're going to arrange an equation again to help us out. When we were computing the velocity of the center of mass, we said that equals the mass of one object times the velocity of that object plus the mass of the next object times the velocity of that object, on, all over the total mass. So let's rewrite that. I'm going to put the total mass over here. Here's the velocity of the center of mass, and that equals m1 v1 plus m2 v2 plus ... And how does that help us picture what's going on? Well, momentum equals mass times velocity. And what we're saying here is that the total mass of a system of objects times the velocity of the center of mass equals the same thing as the sum of all the momenta of all the individual objects. Our system is all of these objects. The momentum of each object is its mass times its velocity. And the sum of all of our momentums, mass times velocity, is the same as the total mass of our system times the speed of the center of mass. Here's a cute little, maybe hard to see illustration of a wrench that has been thrown in outer space. Here's our wrench, and the center of gravity of the wrench, of the object, is close to its head, and it's marked with the little dot. And you can see that the dots are lined up as the wrench rotates. The center of mass of an object or a system of objects will stay at rest or move with constant velocity in a straight line unless acted on by an outside force. And it's in intergalactic space, so there's no outside forces to speak of, so its center of gravity moves in a straight line. If you take that wrench and you give it an initial velocity against our field of gravity, and we track those points of the center of mass will move in a parabola. Because here gravity is the outside force, gravity would cause a stone to move like this, so it would cause the center of mass of any object to move like this. If you have some kind of minor explosive device and you launch it into the air, it will track in a parabola under the influence of gravity. If part way up that device explodes into 4 or 5 different pieces that are all heading away, and you look at the momentum of all the pieces, whether there's 3 of them or 1,000,000 of them, the motion of the center of mass of all of those pieces taken together will still follow that parabolic trajectory, because a system of particles moves as if all of its mass is concentrated at its center of mass. And it moves as if external forces are acting on the center of mass. I saw a cute little problem that we might take a look at, where there was a toy called a hot potato. It was 2 hemispherical pieces connected by a spring. And you put it together, and it clicked together, and at some point it was going to blow apart. So you throw it up in the air, and it goes up and up and up, and at some point this little egg breaks into its 2 pieces that are each heading off in their own direction. Well, what's going to happen? If we picture this parabolic trajectory that it was going to take, the center of mass is still going to follow that same parabolic trajectory. The relative velocity of the 2 pieces will continue, but the center of mass will still continue along there. So one piece is going to come down and is going to hit somewhere here. The other piece is going to come down and is going to hit somewhere here. But their center of mass is going to still follow that parabolic trajectory. Now, when the external force is gravity, as in this situation, we sometimes refer to the center of mass of a system or an object as its center of gravity. And it means exactly the same thing, but it's a term we use when we are looking at how gravity affects our object or our system, as we did right here. And once again, we said that a mass, an object, a system, like bomb fragments, pieces of a hot potato, is operated on by gravity or another external force as if all of its mass is concentrated at the center of gravity, the center of mass, and that's where the force is operating. And you can use that fact to not get confused by a problem like this. Let's say we have a planet with a mass m, and like the Earth, it has a radius of 4,000 miles. And there's a satellite of mass little m that's 10,000 miles above the surface of the planet. And they want to know what the force of gravity is between those 2 objects. Even though we talk about gravity in the upcoming playlist on circular motion, you probably already know that the gravitational force between 2 objects is equal to the gravitational constant times the mass of one object times the mass of the other, divided by the distance between the objects squared. Well, what is the distance here? Is that the distance to the surface of the other object? Or is that the distance to the center of the other object? And the answer is it's the distance to the center. When we're computing gravity, an object acts as if all of its mass is concentrated at its center. So for the purposes of computing a gravitational force, we can replace this entire 4,000-mile radius planet with an object of mass capital M just sitting right here at the center. Now I'll end with two easy, optional, cute things about billiards and bowling. If you have two equal masses, and one has a velocity of v sub naught, and the other is at rest, and the mass comes in and hits perfectly axially, not off center, after the collision, object number 1 will be at rest, and object number 2 will be heading out at exactly the original velocity. That's if the collision is elastic. If you have an elastic collision between two objects of the same mass, picture two billiard balls, but the collision between the billiard balls is elastic. And in fact, billiard ball collisions are very close to elastic. But so you have object number 1 of mass m, and you have object number 2, also of mass m. Mass number 1 is coming in at velocity v sub naught. Object number 2 is at rest. If the collision is elastic, after the collision, object number 1 will be at rest, and object number 2 will be traveling off with the same v sub naught. That's how you make a collision elastic, and the energies before and after the collision add up fine. And you know this from playing billiards, that it seems to happen pretty close to that. And if the elastic collision is off center, if you have object number 1 coming in at v sub naught, and it strikes object number 2 of the same mass, and it lands right here, if the collision is elastic, the post-collision trajectories of these two masses will make a right angle. This will be 90 degrees. And you probably know that from playing billiards also. You plan to hit another ball off center with your cue ball, and you see that the two balls head out 90 degrees to each other. That's if the collision is elastic. And this can be proven, but it's beyond what we're doing in this series. As you know, the total momentum won't change, but this is what happens to the trajectories of the two balls. And we also have, and I'm going to blow this up, this is object number 2, and object number 1 comes in horizontally and strikes it off center. The trajectory of this object number 2 is going to be along the line that connects the centers of the two masses. So object number 2 is going to head off this way, and object number 1 is going to be at right angles to that. And in fact, I found a totally fascinating video of amazing things that happen on the pool table along the topic of the physics of billiards, and I will leave a link to it in the description. Now let's just take a look at bowling very briefly. If you have a bowling ball that comes in and it hits a pin, well, the bowling ball will be deflected by that contact, so it's going to take some angle, and the pin is going to come out at some crazy angle, at some crazy velocity, preserving momentum. But the bowling ball, which is much heavier, is not going to have its trajectory altered very much. We can't count on this being 90 degrees because the masses are different. Does that make sense? If the bowling ball is much more massive than the thing it hits, it's hardly going to notice that it hit it, and it's going to continue on its merry way. maybe only slightly off of its merry way. So what's the point of all that? Many bowlers like to bowl with heavier balls. They can be harder to swing and harder to get a good velocity with your swing, but the trajectory of the bowling ball after contact with the pin can be a little bit more predictable if you expect it to deflect less after it hits the pin. And that's one of the pros and cons that bowlers talk about when they're deciding what weight of ball to use. If you have a difficult spare to pick up among the 10 pins, and you want to plan where the ball is going to go as it heads deep into that triangle, you can plan a little bit better with a heavier ball. So as always, thank you for your attention. You may leave comments in the comments section or send me emails. In the next video, or perhaps couple of videos, we will work some problems which will reinforce these concepts about momentum and show you how to handle some of the free response questions from recent AP Physics exams. Thank you.